Good morning. Assalamualaikum warahmatullahi wabarakatuh. Hadaria again. This is my lecture number 6, if I'm not mistaken, for CHM676. In lecture 5, I introduced you to olefin. Uh, Olefins are ligands that donate their pi electrons to metals to make organometallic compounds or organometallic complexes called olefin complexes. So one of the most famous olefins is cyclopentadiene complexes, which has a structure like this. Now, this is cyclopentadiene anion, which actually is derived from the diene, which is cyclopentadiene. So when cyclopentadiene lost one of the protons at the top here, either this one or that one, so this will have reached aromaticity, yeah, C5H5, and it is mildly acidic, and this cyclopentadiene is mildly acidic and loses a proton, producing cyclopentadiene anion. Now, sometimes this is called CP, given the symbol CP. Now, cyclopentadiene complexes are of great historical importance because in the 1950s, the renaissance of inorganic chemistry started with the discovery of a sandwich compound, ferrocene, which is this one, eta 5C5H5 2, an ion, which is commonly written as CP2Fe, where CP is cyclopentadienyl. It was discovered simultaneously by two researchers, Wilkinson and Pawson, both of whom were working independently. Wilkinson then won a Nobel Prize for this work on ferrocene. Now, what is a ferrocene? Ferrocene is an orange solid which melts around 170 degrees Celsius with sublimation. That means it doesn't become liquid. It changes from solid to gas at 170 degrees Celsius. It is a 6-electron donor ligand. It is diamagnetic. That means it doesn't have any unpaired electrons in it. It is easily oxidized to blue Cp2Fe plus, yeah, losing one electron, having one unpaired electron. In solid state, it has planar cyclopentadienyl rings with all the CC distances equal. Yeah, the rings are arranged in staggered sandwich configuration rather than eclipsed. In gas phase, ferrocene has eclipse configuration. It indicates that the energy barrier to ring-free rotation is quite small, which is about only 5 kilojoule per mole. So in solid, it has this staggered. What do I mean by staggered? It means that this carbon at the back of this cyclopentadienyl ring at the top is positioned above this distance between two carbons, and vice versa. This point is in between there. So this is in solid state. It has staggered configuration. The reason why in solid state ferrocene adopts a a staggered configuration is because it actually is the most economical packing to uh, minimize repulsion. Yeah, if you imagine there is a bump of carbon here, in between the two bumps at the top there is a trough. Yeah, there is a lekuk, a trough. So the bump and the trough will make a good packing and less repulsion. But that is in solid state where the volume is limited. But when it exists in a gaseous phase, where the volume of the space where this can occupy is not an issue, because in gaseous state you have huge amount of volume. It's okay for the two CP at the top and the bottom to exist as eclipse configuration, where bump is on top of bump and trough is on top of trough, because you have huge amount of space or volume to occupy in the gaseous state, as opposed to a limited amount of space to occupy in the solid state. Now, X-ray crystal structure shows that ferrocene is a highly symmetrical sandwich compound, with all the 10 hydrogens or 10 protons being identical, having one signal in the proton NMR spectrum. So if you run an NMR spectroscopy on ferrocene, what you will see is just one single peak that um, uh, is the signal for all the protons in there. They are all identical. Researchers have since produced and still are producing thousands of cyclopentadiene complexes with other metals, and these are known collectively as metallocenes. Yeah? Ferrocene is having iron in it. If you have other metals, then you call it metallocenes. All the first row transition metals except titanium have formed CP2M complexes, and many from the second and third row have done so as well. Yeah, you can see that in the table 583 in the textbook Douglas. Now, the C5H5 minus anion and ferrocene contain aromatic 6-pi electron ring. The rings in ferrocene react easily by electrophilic substitution like benzene. It is possible to replace all the protons in CP with methyl to produce C5 CH35 minus. And this substituted cyclopentadiene ligand is very common in the field of organometallic chemistry, and it is given the symbol of CP star. Yeah, star for methyl. This is what I was talking about in my lecture 5 when I went through the table at the top here. There is a table here. We have, excuse me. Yep, you have CP cyclopentadienyl here, and CP star as pentamethyl cyclopentadienyl. Back to the ferrocene. CP complexes containing other ligands are also common, because CP rings can bend back to make orbitals sterically available for bonding to other ligands. Sometimes only one CP ring complexes to a metal, acting as a 6-electron donor occupying 3 coordination position. The other positions can be occupied by other ligands, producing half sandwich complexes. Yeah, there are so many different ways that researchers have experimented on cyclopentadienyl. An example of the application of ferrocene derivatives is the Exactech pen meter, which is used to measure blood glucose levels quickly and simply. So the derivative of ferrocene have helped a lot of diabetic sufferers to monitor their blood sugar level. It takes only 30 seconds for blood glucose reading to be determined, and virtually it eliminates user errors commonly associated with color reagent test strips. Now, many diabetes out there are benefiting a lot from this technology, and that is why the discoverer of ferrocene, who is Sir Geoffrey Wilkinson, have received a Nobel Prize, along with another researcher who was also working on ferrocene called Fisher. Yeah, so Fisher and Wilkinson have both received a Nobel Prize for their work in ferrocene. Yeah. So that is about ferrocene. Next topic is about experimental evidence for back donation. This is a different topic altogether. This is just to see what actually have prompted scientists to come up with the idea of pi back donation. If you can still recall, uh, the bonding of carbon monoxide to metal divided into two parts. The first part is the um, sigma donation, where the lone pair of electrons in HOMO is donated to the metal, and this donation prompted the metal center to do pi back donation because metals are electropositive moieties. They do not like having high electron density around them, so they back donation. They donate back the electrons onto the LUMO of your carbon monoxide. And this is called a pi back donation because the overlap of orbital in this back donation is overlapping side to side, so making a pi bond. So how do we prove that pi back donation has occurred? So we can look into a few experimental evidence for pi back donation. So this is what I said just now. You have the sigma donation for carbon monoxide to metal, where the lone pair of electrons on carbon is donated to the metal, and pi back donation when the excess electrons on metal is being donated back onto the LUMO of carbon monoxide and the synergic effect. So the two types of bonding, which is the sigma bonding and the pi back bonding, they are cooperative. And this type of bonding is not only unique to carbon monoxide, it also applies to other pi acceptor ligands. And the net effect on carbon monoxide is that the electron density is removed from the weakly bonding sigma, yeah, sigma 3, and increase the electron density in the strongly antibonding pi 2 level. So if you can recall about our HOMO and LUMO of carbon monoxide, you will understand this very, very well. Therefore, if you want to see what is actually the effect of pi back donation to any carbonyl complex, you are looking to see that the metal to carbon bond would become stronger and shorter than a normal single bond, and the carbon to oxygen bond would become weaker and longer than a normal triple bond. Why is the CO bond become weaker and longer? That is because pi back donation populates the LUMO, which happens to be an antibonding molecular orbital. Putting electrons in the antibonding molecular orbital will lower the bond order of CO, because bond order is the sum of bonding electron minus the sum of antibonding electron divided by 2. So if the sum of antibonding electron is high, then your bond order will become low. Yeah. So when there is pi antibonding happening, you expect to see that the carbon monoxide will become weaker. The bond between carbon and oxygen will become weaker, and that bond will become longer than a normal triple bond, triple C triple bond O. And because the pi back donation is such that uh, there is a flow of electrons from metal to carbon, so this metal to carbon bond becomes stronger than just a single sigma bond. So there is a pi bond on top of the sigma bond here, making this MC bond stronger, and there is a lowering of bond order on your CO, making the CO bond weaker and longer. Right, so this is what we will be looking for if we want to look at the evidence for pi-back donation. So experimental evidence can be obtained. So experimental evidence for pi-back donation can be obtained from the X-ray results for bond length and from the infrared stretching frequencies which reflect bond strength. Now let's have a look at infrared first. Now, when you look for evidence in the infrared spectroscopy, you have to bear in mind the Planck's equation. Now, the Planck's equation is energy equals to a constant, a Planck's constant, multiplied by the frequency, or hc over lambda. This is a very, very common and very well-known equation for scientists. So there is a relationship between the energy of the bond with the frequency at which the vibration appears in the infrared. So if the bond has a high energy, or it is a strong bond, then the frequency is expected to be high as well. And if the bond is weak bond, then the frequency will become lower as well, according to the Planck's equation. Now, energy is proportional to the frequency of the vibration, of the infrared vibration, i.e. the stronger the bond, the higher the stretching frequency. So if you look at, just 1 second, if you look at this only for the time being, just focus on, 1 second. Yep. Just focus on the boxed information. For free carbon monoxide gas, the stretching frequency of CO is found at 2143 centimeters minus 1. So it is quite high on the infrared spectrum, and it is reflecting the triple bond that you expect to see between C to O. Yeah, there is a triple bond, so it's quite a strong bond. But let's have a look at chromium first. Oops. Let's have a look at chromium first. When chromium is bonded to carbon monoxide, the stretching frequency of the carbon monoxide can be found at 2000 centimeters minus 1. So there is definitely, comparing between the blue, I'm putting this as color blue for now. Yep. Oh, that's not a good blue. Let's have a look at the more vibrant blue like that. Okay. If you look at the blue writing here, the stretching frequency of free carbon monoxide is 2143, but when carbon monoxide is bonded to chromium, the stretching frequency is shifted to lower frequency. That means there is a weakening in the bond. So that is a good evidence of something happening in CrCO6 that makes the carbon monoxide bond becomes, or the CO bond becomes weaker because it has lower frequency. So that is actually the evidence for pi-back bonding, because in here we are already saying that theoretically we are expecting that the CO bond will become weaker and longer than the normal triple bond. And yes, we have seen that the CO frequency of the, CrCO6 has a lower frequency than the free. And if you look at here, the stretching frequency for metal to carbon bond, you find it to appear. There was none before. Yeah, when you have a free when you have a free carbon monoxide, obviously you will not expect to have a metal to carbon bond because there is none. There is none. So, but when you are reacting chromium to carbon monoxide, you're going to have a new peak that appears in 441 centimeters minus 1. So there is definitely, this is definitely an evidence of pi-back bonding that happens between metal to carbon of your carbonyl complexes. So that is fine. Don't want to go on holiday now. Okay, that is fine for a free carbon monoxide compared to the chromium CO6. But if you change from chromium CO6 into manganese CO6 plus or VCO6 minus, there are also some changes that is observed, some changes that are observed by scientists. So what do those changes signify? So I'm going to go through this slowly with you. Here. Of the three organometals here, the manganese, the chromium, the vanadium carbonyls, of the three, VCO6 minus has the metal with the smallest nuclear charge. What do I mean by the smallest nuclear charge? That means that vanadium, how do we determine that it has the smallest nuclear charge? Let's go through this table together. I'm comparing CrCO6 with MnCO6 plus and VCO6 minus. Why do we put these three species together? It is because we would like to make them isoelectronic. Isoelectronic means that they have the same number of electrons, right? So let's go through the table. So you are going to be able to see what this paragraph at the top means after we go through the table together. So look at the metal center, manganese, chromium, and vanadium. What is the atomic number of the metal center? If you go through a periodic table, you will find that manganese has atomic number of 25, chromium has atomic number of 24, and vanadium has atomic number of 23. And obviously, in the nucleus of any atom, you are going to have that same number of protons as well. So the charge of the nucleus of manganese is 25 plus, because there are 25 electrons in the orbitals of manganese, and to make a neutral manganese, the the nucleus has 25 protons, which carry with it 25 plus charge. And on the same argument, chromium with atomic number of 24 has 24 plus charge in the nucleus, and vanadium with atomic number of 23 has 23 plus charge of the nucleus. Now, the number of electrons of the metal center. Now, chromium 24 obviously has 24 electrons on the outside in the orbitals, right? To offset the nuclear charge. So 24 protons in the nucleus, 24 electrons in the orbitals, you're going to have a neutral chromium. But if you have a manganese plus, because carbon monoxide here doesn't carry with it any charge, you're going to have manganese with a +1 oxidation state there. You are actually losing one of these electrons here. You're losing one of the electrons here because it's a plus charge species. So manganese plus also has 24 electrons. Vanadium minus, on the other hand, also has 24 electrons. This example is highlighting the fact that all the metals are isoelectronic, having the same number of electrons. So we can actually see the effect of other things except for this isoelectronic. Now, if you can imagine having 24 protons. Imagine chromium first, having 24 protons in the nucleus and 24 electrons in the orbitals. You are going to immediately see that each proton will be paired up with one electron. So there will be no surplus, and you're going to have a nicely neutral compound. But if you have MnCO6 plus, you are having 25 plus charge in the nucleus, but only 24 electrons in the orbitals. So what you are having is an excess of protons in the nucleus. Yeah, excess of proton, one excess. That means the electrons are bound tighter together because there is an extra plus charge in the nucleus that binds 24 electrons. 25 plus pulling in 24 minus, making that attraction between the nucleus and the electrons in the orbital very, very strong, as opposed to this VCO6 minus. In vanadium, you have only 23 protons in the nucleus, but vanadium has this vanadium minus has 24 electrons on the outside or in the orbitals. So 23 plus in the nucleus pulling 24 electrons. You're going to see that the attraction between the nucleus and the electrons here is going to be slightly less than that in here. So the strength of attraction of metal electrons to the nucleus, you're going to see that for manganese, it is most tightly held by the nucleus, 25 plus versus 24 minus. And for the vanadium, it is least tightly held by the nucleus. The electrons are least tightly held by the nucleus. 23 plus in the nucleus and 24 minus electrons on the outside. So not held very tightly at all. So this is very, very tightly held in the manganese. In the vanadium, it is a bit loose, but the chromium is intermediate. Now, when you are talking about pi-back bonding, you are always looking at electrons that are in the metal center. So, when you have most tightly held electrons by the nucleus, obviously those electrons will not be easily given away in pi-back bonding as opposed to your vanadium, because in the vanadium the electrons, the 24 electrons are not very, very strongly held, so it is going to be able to do pi-back bonding a lot easier than the manganese. So you're going to have highest degree of pi-back bonding in the vanadium compared to the manganese in this case. That means with the pi-back bonding occurring a lot for this vanadium, the LUMO of this CO here, this is the CO that has a LUMO, it's going to have the highest amount of electron density, whereas the manganese will have the lowest amount of electron density because there's not much pi-back bonding happening. And for vanadium, the bond order of your CO will be the lowest because it has a lot of electron in the pi antibonding molecular orbital of the LUMO here. So that's lowest bond order, highest bond order for manganese. Accordingly, with the low bond order, you're going to have a low bond strength, the low strength of CO, hence the low stretching frequency of CO, and obviously anything that is a strong bond will have anything which is a weak bond will have a longer bond. Yeah, a weak bond is a long bond, a strong bond is a short bond. Yeah, so that is the explanation why the stretching frequency, the new CO in MnCO6 plus is high compared to the stretching frequency of CO in VCO6 minus. Yep. So once you understand this table, we're going to be able to read this paragraph quite effectively. VCO6 minus has the metal with the smallest nuclear charge. Here is the smallest nuclear charge. That means vanadium has the weakest ability to attract electrons and the greatest tendency to backdonate electron density to CO, i.e. populating the LUMO of the CO that happens to be pi antibonding. Should be symbol that happens to be pi antibonding, which is an antibonding molecular orbital. The consequence of high electron density on pi antibonding LUMO and reduction of bond order and strength of the CO will lower the new CO because the frequency is directly proportional to energy, right? So I hope you understand this trend. You having the stretching frequency of your CO in MnCO6 plus to be higher than that in chromium CO6, but uh, the lowest one is VCO6 minus. You are going to be able to explain this trend by just looking at this table, the explanation behind it, as well as this paragraph. And obviously, the degree of pi back bonding is also reflected through the strength of metal to carbon bond. The more pi back bonding, the stronger that metal. There you are. This is a lot of pi back bonding happening in your vanadium. You have the metal to carbon bond to be strongest, followed by CrCO6, and then the weakest metal to carbon bond is found in MnCO6 plus because the degree of pi back bonding in MnCO6 plus is low. Low because of this. Yeah. I hope that is easily followed by you, the argument and the explanation. So in general, the more negative the charge of the organometallic species, the greater the tendency of the metal to donate the electrons to the pi antibonding LUMO of CO, and the lower the energy of the CO stretching vibration. Now the trend with metal to carbon bond is exactly opposite to that of the CO bond. The stronger the pi back bonding, the stronger the CM bond, and the higher the new MC. In the case of free CO, there is no pi back bonding occurring, obviously, because there's no metal, so there's no pi back bonding. The pi antibonding LUMO, excuse me, this is still not similar. The pi antibonding LUMO is not populated with electrons. The bond order is high, and the CO stretching vibration has a higher energy, reflecting the strong triple bond. Yeah. Now, if we are looking at the free CO that has the highest bond dissociation energy, or for the triple bond, it is having the highest frequency followed by CO with one metal atom. Okay, now you can also have bridging because we have met bridging bridging CO before. Yes, in lectures 2, I think we have bridging CO. Now, if you have a free CO, you compare it with terminal CO, the stretching frequency, and compare those two with the bridging CO frequency, you are going to see that the bridging CO will have the lowest stretching frequency because it has the highest number of pi back bonding, because there are two metals making a pi back bonding to that bridging CO. You have metal on the right making pi back bonding, you have metal on the left making pi back bonding, making the CO, the bridging CO, having the highest degree, receiving the highest degree of pi back bonding, the lowest stretching frequency, the weakest CO among the three, among free and terminal and bridging, and the longest bond. So that is, you can also use the value of stretching frequency to determine whether your carbon monoxide is a free carbon monoxide unbonded or a terminal carbon monoxide bonded with only one metal, or bridging carbon monoxide bonded with two metals. Yeah, just by looking at the value of your stretching frequencies or new CO. Okay, so that is the evidence for pi-back bonding. And similar thing can also be observed not only in carbonyl complexes but also in olefin complexes. Similar. Because we have from the Dewar, Chat, and Duncanson model, they also propose that the alkene is bonding to the metal through sigma donation first and then pi back donation followed by pi back donation, and the synergic effect of sigma donation and the pi back donation is very similar with the carbonyl. So you are also going to expect similar things or similar observation. So what is the effect of pi back bonding on C double bond C? The sigma donation here, this is the sigma donation where the um, pi electron on Cc is donated to the metal. The sigma donation will remove electron density from the Cc pi bonding HOMO, and the pi back donation will place electron density in the Cc pi antibonding LUMO, and the net effect will have lower the Cc bond order. So the prediction is there will be a weaker and longer Cc bond when olefin is attached or bonded to a metal center. So experimental evidence. Is our prediction is in agreement with the experimental evidence? So experimentally, the Cc bond is seen to be weakened or made it less strong when it becomes a complex with the transition metal. Free ethene has a Cc bond length of 1.34 angstrom, but the C double bond C in the Zeiss salt, if you can still recall the Zeiss salt, it is a slightly longer bond length, which is 1.38. So this C double bond C in the Zeiss salt is weaker and longer than the C double bond C in a free ethene. And that is similarly manifested in the infrared stretching frequency of C double bond C, where you see there is a drop as well. The free ethene has a stretching frequency for C double bond C at 1623, whereas in the Zeiss salt, you have the ethene bonded to platinum. You have the stretching frequency of C double bond C to be in a lower position, in a lower frequency of 1516. So reducing from 1623 in the free and 1516 in the bonded. So that is also an evidence of pi back donation happening in the olefin complexes. Right. So we have covered up to infrared. So I'm going to leave it at that for this lecture. And I'm going to see you next in my next lecture when we are talking about other things. Okay. Before I end, another one, just a quick one. Of course. No, no, no. I'm not going to start for this one. I'm going to make it for the next lecture. So that's it. Thank you very much. I hope my lecture is clear and you can understand this reasoning very well. And all the very best. Keep safe, study well, and take care. Assalamualaikum.